Okay, where was I with that? Oh yeah, okay. So as we were saying, the distance sensor encompasses not only ultrasonic sensors, but infrared sensors and any other kind of distance sensor as well. So in this case, all we're gonna do is make a pointer to, well, a pointer or an array of pointers to 8 different distance sensors. And how we set it up is that we simply use a loop in the main body to actually iterate through every single sensor we want to get as well as enable and store it within the pointer to the distance sensor. And if you're not familiar with pointers, that's fine. This is just to make it easier in order to index the distance sensors instead of having each one have an individual name. And once again, if you go on to the Cyberbotics manual reference guide, they list out all of the positions of the distance sensors. So for the first 8 sensors, these are the front sensors, and then the other 8 are the back sensors. So if we index the first 8, we're essentially only getting the first 8 front sensors. And all of them are called SO0, SO1, SO2. So what we do is just get the distance sensor with SO, and then we concatenate a string of the index onto there. All right. And like I said before, the value of the distance sensor is not a pure distance. It's actually dependent on what Webots uses called a lookup table to map simulated distance to the sensor value. So if I pull up that lookup table, this is an example of a lookup table. So Webots actually allows you to add noise to your sensors to simulate a real all the way, and if I move this, it increases all the way up to around 1023, where it just stops increasing from that point on. So the range of this sensor is just from 0 to 1023, and that's not dependent on any actual distance. This is not representative of a distance itself in terms of units. You have to find whatever value you want to set as a threshold yourself. Okay, and next is the GPS. So I'm going to stop the simulation. The thing that's useful about the GPS is that it just gives you your absolute position within the world. And that position is actually based off of something in the world info node called the GPS reference point. And right now it's set to 000. And what that point is for is that whenever you have a GPS, your position of the GPS is always relative to that point. And since it's a world origin, it's simply going to be the translation of all of the robots in the first place. So in this case, the translation of this robot is this. If I were to print out the GPS reading of the X and Z, because we don't care about the Y is the height. Then you can see that the translation actually matches the position of the GPS. So that's useful for localizing yourself within the map, and it's going to help greatly with your navigation. All right, and finally, we're going to talk briefly about the camera, and we're going to go over camera recognition more in the next video because we're going to do victim retrieval in that video. So the camera is slightly different than the other sensors because of a few things. First of all, you have your own window up here in order to view the camera view. And you'll notice that we have 2 of these. So one of these is associated with each camera. So there's one camera on this robot and another camera on the other robot. And this camera view is associated with robot 1. And this camera view actually only pops up when you actually enable the camera. Otherwise, it's going to be black. So You'll also notice that we have these red boxes within the camera view. That's because Webots has an automatic camera recognition feature. Webots allows you to recognize objects using a camera based off of a color property they have. So if I run the simulation, this magenta block, for instance, it has a color property of 101. So this is its quote unquote color that the camera sees whenever you point your camera at it. And if I move it in front, then it draws a red box around the magenta block, which means that the camera is recognizing it. So if I wanted to, I could extract information from the recognized objects that the camera sees. And how we do that is, first of all, we have to call this function camera get recognition objects, and that returns a pointer to the objects you have. And then once again, you can index it like an array. So all I'm doing here is if I'm saying, if I have more, at least one object that the camera sees, simply print out the position of the first object it sees, and that's just the X and Z coordinates. Other things you could do with a camera, if I pull it up, is, all right. You can get not only the position, but the orientation, as well as size, position on an image, size on image, etc. And this position and orientation is actually in reference to the camera's location, not the world location, but specifically the camera location. And once again, getting the position is very useful if you want to perform victim retrieval, since you need to approach the victim, first recognize it, and then approach it using the position given by the camera. All right, and we can try that. Okay, so if we move right in front of a block, the position is getting smaller and smaller as you approach the block, and then we're going to pick it up eventually once we stay next to the block. Okay, and one more thing that you can do with cameras is you can actually take the camera image and apply vision processing using libraries like OpenCV. And we're not going to cover that because that's obviously very advanced for the simulation game. You're not going to need OpenCV in order to play this game because all the camera recognition is once again done by Webots for you. But if you're interested, there's a nice sample world that Webots has that demonstrates this feature. So if you open sample world and you go under samples, how to, and vision, it's going to open up this world as well as the code they use to run this world. And this is just an example for their integrating OpenCV along with Webots. And take a look at that on your own free time if you're interested. Once again, it's not anything mandatory. And finally, we have a couple other sensors called light sensor, receiver, and emitter that we didn't go over. So the receiver and emitter are just for communication between robots or anything that has a receiver or emitter as well. And the light sensor, it's not a normal NXT or EV3 light sensor where you can tell the reflected light off of a surface. And normally you'd use that for like line tracing by, since white reflects more light than black. this is not the same thing. It doesn't work like that. This light sensor is specifically for telling the light from light sources within the simulation. It does not tell you the light reflected on a surface. So you can say see that it says it detects the light emitted by point light, spotlight, and directional light nodes. So those are within your simulation. They're not based off of reflection of a surface. And that's for all of the sensors on the robot.
So Victor just went through all the individual sensors that you're going to need for Webots. For those of you using Python, it's actually very similar to the code in C++. So if I share my screen, we hop over here. So this is the sample code for using the GPS sensor in Webots. So if you remember from the C++ section, you need pretty much 4 basic lines of code to make your sensor run. And in Python, it's pretty much the same. First off, you need an import. So you just do from controller import GPS. And GPS is going to be the type of sensor. So like we said before, inside the scene tree, you have the type of sensor on the left-hand side and the name of the sensor on the right-hand side. So this is just a type of sensor. Then over here, you create a GPS sensor object. So you have an object named GPS. You do a myrobot.getGPS, and this function or this method name is the same as in C++. If you go back to the documentation, sorry, I couldn't find it before, but here it is under the robot section. If you scroll about 1/3 of the way down, then you will get this list of all the get methods. This is for C++, but if I hop over to Python, the names are all pretty much the same. So if I find get GPS right here, and if you need any other sensor, you can just scroll down on this list and it should be on here. So that's how you create your GPS sensor object. Then same thing as C++, you do a GPS.enable and you pass in your time step. Then you can just do a GPS.getValues, and it works the exact same way as in C++. So that's pretty much it. Just remember the 4 basic lines of code in both C++ and Python. It's just to include/import statement, create a sensor object, enable the sensor, and then you can perform a get values on it. And all the information about the enable or the get values methods are all in the documentation. If you go under your sensor, so I'm going to find the GPS sensor, GPS, then I can see all the information that you might need all right here. And remember, I can always switch from C++ to Python, and it gives you all the available GPS methods that you will need. And that pretty much covers it for sensors in Webots. I guess we're going to start taking questions then. So if you have any questions, make sure you send them to the moderator over the chat function in Zoom.
Oh yeah, and one more thing I wanted to show that I didn't get to show in the video. If you want to add your own sensors to play around with beyond these sensors, you can actually add them by hitting Add New. And under base nodes, there's a variety of other sensors that you can play around with. For instance, there's accelerometers, compass, LiDAR actually, and a bunch of other sensors. So if you want to play around with other sensors within Webots, feel free to do so. You just add it under extension slot. You're not necessarily going to be able to have those sensors in the actual competition, but just for fun, if you want to experiment around, go ahead.
Okay, Jeffrey, you there?
Yep.
Okay. I'm sorry, I was in the middle of talking to Elizabeth about something. Are there any, I see there's one question from Derek. Hold on one second. And here, I can't paste that for some reason. Derek asks, well, he just basically asked, can you talk more later to simulation of noise? I believe that's pertaining to the gyro. Remember how you guys were talking about noise earlier?
Yeah, so
okay.
noise, there's no plan to add like noise to the competition itself. But if you're interested for yourself, I guess we can talk later after the meeting's done about noise, but any information you might need, if I can share my screen real quick. Anything you might need to know about noise, each sensor has its own section on noise. So you can see this is for GPS. It tells you how it calculates all the noise. So you can just read over that. It's not that long. So it should tell you pretty much what you need to know. But if you're gonna do the actual competition, then noise should not be that big of a problem, if it is a problem at all.
Yes, I think the current gyro or the current sensors in general, they are pretty much set to noise free as of right now.
And you guys can confirm, I mean, do you know for the competition if that's definitely going to be turned off? I imagine it would be.
Yeah, we don't know. You can set the level of noise you want, so I have no idea if they're going to change anything about that.
As of right now, it's set to no noise though.
Yeah.
Yeah.
Okay. Because normally, like for the actual, like if you get the sensors, let's say from Adafruit or somewhere else, they normally do like Kalman filtering and stuff like that to get rid of a lot of the noise to begin with that you would end up having to deal with. So you end up, I mean, so like if you have an IMU hooked up, it works really well. I mean, at least within the last 3 to 4 years, from a programmer standpoint, they've been close to noiseless to begin with. So I can't imagine them introducing that into a competition. Okay. All right. Is there anything else, Jeffrey, Victor? Oh, wait. Oh, wait, they do their own hidden Kalman filter. That's super cool. Yeah. Yeah, if you look at some of the Adafruit libraries, I think for the Bosch IMU, the Bosch BN0055, I think they have, yeah, you guys use that. I think they do Kalman filtering. Actually, they might do that on the chip. Let me take that back. That might be done actually on the chip for that particular sensor. I know that the SparkFun sensor, the old one, those old Razer IMUs, the one where you had to do all the calculation. So they'd give you 3 different sensors, compass, gyro, and accelerometer. And you basically would cook the data, and then they do noise filtering in the code itself. So yeah. My son actually gave a talk about that because that's sort of like his bread and butter. He does guidance, navigation, and control for satellites. So he gave a talk at Storming Robots a while back on how to deal with noise. Should have videotaped it, but we didn't at the time. Maybe I can get him to do it again. All right. So are there any questions from anyone?
Remember, it doesn't have to be about just this week. If you have anything about the past 2 tutorials,
yeah,
we're open to questions about that too. Anything in general.
Okay. All right then. So just a reminder, the next week for Saturday, I'm going to bring it up. I'll share the screen real fast. Okay, hold on. If you all recall, let me hold on one second here. So if you recall, if you go to stormingrobots.com, go to the main web page and click on Webots Simulation Group. You can come down here, you'll see the schedule. This was last week. I'm sorry, this was last time. This was last Wednesday. This was today. And next week, learn the fundamentals required to detect various objects. So that'll be on June 6th. That's next Saturday at 10 a.m. All right.